Hello everyone, and welcome to this course on electromagnetic interference and electromagnetic compatibility for power electronics engineers. My name is Abhijit Kshirsagar, and I will be presenting this material in a 3-lecture series consisting of 3 videos. In the first part, we are going to be talking about some introduction to EMI, EMC, and some basic concepts and some electromagnetics review. In the subsequent videos, we'll take over some case studies and evaluate EMI, EMC issues and solutions to the same in each circuit. In this video, we are going to first begin with an introduction to EMI and EMC. First, let us look at some terms and definitions. The first term we come across is EMI, which is electromagnetic interference. The next term is EMC, which stands for electromagnetic compatibility. Now, first we need to look at the word electromagnetic. Maxwell's laws tell us that electric and magnetic phenomena are related. Electric fields can give rise to H fields, that is magnetic fields, and magnetic fields can give rise to electric fields. And Maxwell's laws tell us how and when that can occur. Depending on the circumstances of our circuit, we may need to look at both electrical or magnetic phenomena, or just one of the two. The next term that we can look at is interference. The English definition of the word interference is a hindrance or disruption of intended operation. In the EMI and EMC context, it refers to disruption of the intended operation of a system as a result of incident electromagnetic energy. Another related term is noise. Now we know from Shannon's work that all signal or all information is equivalent to energy. And whenever we transmit information, we are basically transmitting energy. And any undesirable interference or disturbance in that information degrades the signal or information that we are trying to transmit, and that constitutes noise. And as a result, any undesirable energy in the system can result in degradation of our signal. The last term we need to look at is called compatibility. Compatibility, again the English definition, means the ability to coexist. In the EMI and EMC context, it means that multiple pieces of equipment or electronic systems can coexist without causing interference or hindrance to each other. And this particularly refers to the amount of electromagnetic energy emitted and absorbed by the systems. Compatibility consists of 2 aspects. The first is emissions. For instance, in order to have good compatibility, a piece of equipment should emit the minimum amount of electromagnetic energy when it is operating. The other side of compatibility is immunity, which refers to immunity to incident electromagnetic radiation. A good piece of electrical or electronic equipment must be able to operate even when there is some amount of incident electromagnetic energy. We'll look at these things in detail as we go on. Now let's look at some sources of electromagnetic emissions. Where does this electromagnetic energy come from? The first, of course, are natural sources. We all know that lightning and electrical storms give off a lot of electrical energy, electromagnetic energy, that is. We also have sources of EM radiation outside our planet. Solar flares and cosmic EM radiation are the most common sources. And as you can imagine, these sources are most severe or most critical for equipment such as aerospace, military, and space applications. The other sources of electromagnetic energy can be classified as human sources or anthropogenic. And these consist of 2 categories. One are unintentional sources, of electromagnetic energy, which means that these are systems or components which are not intended to radiate or intended to emit electromagnetic energy, but they do. One very common example is power lines. Power lines carry a huge amount of power at high voltage and high current, and as a result, they set up an electromagnetic field around the conductors. Now, most power line transmission of electricity is at low frequencies, 50 or 60 hertz. But because the size of the transmission line is so large, that can affect the emission of electromagnetic energy, and we'll see this in detail a little later. Another common source of electromagnetic emission, unintended electromagnetic radiation, is motors. We have a number of motors that contain brushes, and every time a contact is made or broken, there may be some arcing, and that arc constitutes a source of electromagnetic radiation. Similarly, transformers, they have stray electromagnetic fields, and some of this field can link to nearby systems. Another example of unintended sources of emission are high-speed digital communication cables. For instance, USB and HDMI. These days, even though these are wired forms of communication, the data speeds are so high that some amount of energy is emitted by the cables or the conductors that carry these signals as well. And the final source of EM emissions, which are probably the most numerous, are the intentional sources. These days, wireless communication is omnipresent. We have cell phones, satellite communication, Wi-Fi, and a number of other personal electronic devices that transmit in the wireless bands, such as Bluetooth, Zigbee, etc. And all of these are intentionally transmitting electromagnetic energy as part of their functionality, which means for communication. And this energy can couple with other systems which are nearby and cause unintended operation. Now let's look at some motivations for looking at EMI and EMC. Why should we consider EMI and EMC issues at all? The first aspect, of course, is product functionality. As designers or product designers or system designers, we design products to meet certain functional requirements. The product must be able to complete certain functions, must be able to operate in a certain way, etc. And the product must have a good efficacy, which means the effectiveness of the product in the intended or expected environment must be good. For instance, if we are making a Bluetooth speaker that is supposed to work with cell phones around it, we expect that cell phones are emitting electromagnetic radiation as part of the normal operation, which is calling or texting. And so the Bluetooth speaker must be able to withstand, or in other words, should not be affected by the EM radiation coming from the cell phone. Another example is that speakers or amplifiers that are used, say, in an on-stage application, these also must not be affected by the radiation from the mains wiring that may be nearby, and so on. Then the other thing to look at is accuracy and precision in a system. This refers mostly to measurement and control systems. For instance, in an industrial environment, supposing we have a current measurement system, say that is measuring the current in a motor or something like that, we expect that because there is so much industrial equipment around, there will be a lot of EM noise, as we talked before. And so, in order to be able to operate correctly, to measure correctly with good accuracy and precision, the system must be able to reject all incident electromagnetic noise. And the final thing is overall quality of the product. Even if the product is not completely hampered by incident EM noise, or its performance is only marginally degraded, that can degrade the user experience. And this applies especially to consumer electronics these days. So the next aspect of EMI and EMC is, of course, sales. the object of most engineering is to develop a product that will be sold to consumers or customers. And in order to be able to sell a product in a given country or in a given market, there are some statutory EMI and EMC rules, which means that the standards body sets up certain rules and regulations which new products must adhere to. And part of those rules apply to EMI and EMC. And the other thing to look at is that these apply not only to current rules in current markets, but future markets and future rules as well. So as a good designer, one must design the product to meet not only today's requirements in today's markets, but future requirements in future markets as well. For instance, if you're trying to sell a product in the United States, the ruling body for these standards in the US is called the FCC, the Federal Communications Commission. And so the product must meet those requirements. The other thing to look at is that we often sell products which will interact with other systems or devices, and any incompatibility with other devices will again affect sales. So we want to make sure that the device that we are designing or selling is not going to cause compatibility issues with other devices that the consumer or customer may already have. Again, as I mentioned before, keeping EMI as low as possible, the amount of energy radiated, keeping that as low as possible ensures that it minimizes the possibility that some compatibility issues will come up. That for all good products, EMI and EMC considerations must be included in the design cycle from the beginning and must not be tacked on at the end of the design cycle. This is just a summary of some regulatory bodies that exist around the world. You can see that depending on the country and sometimes even depending on the application, the standards that apply and the body that applies these standards can change. For instance, we have Department of Defense and Federal Communications Commission in the United States. In Europe, there is the IEC and CISPR. Similarly, we have organizations in Brazil, India, and so on. I just would like to point out that depending on the target market, the designer must figure out what are the standards that apply and how to design the product so that they meet those standards. It should also be noted that not all these standards are identical, and there is some difference in how these standards are applied. There is some work underway where all these countries are trying to agree to a common set of standards, so designers do not have to redesign or change their products in any way to meet standards of different countries. The idea is that if there is a common standard, a product that is designed to meet the standard in one country should automatically meet the standards in all other countries. And that is called harmonization of standards. Now let's look at emissions and susceptibility, which are two sides of the electromagnetic compatibility that we talked about earlier. They are somewhat two sides of the same coin in some sense. Now, emissions requirements basically talk about how much electromagnetic energy can be radiated or emitted by a product. There are limits on both conducted and radiated noise. We'll see what conducted and radiated noise mean in later slides. There are limits on spectral densities, which means what is the frequency spectrum of the noise that is being emitted. There are limits on temporal density, which means how much noise can be emitted as a function of time. And these are often enforced by the standards body, for instance, the FCC or CISPR, etc. They can also be enforced by the customer, because if a customer wants a low noise, has a low noise requirement, then these can be enforced by the customer as well. On the other hand, susceptibility requirements come from the product designer's motivation to limit disruption in the system due to incident noise. They are usually not governed by the standard, but they are governed by the intended application and the design constraints. Sometimes they can be a key requirement, for instance, in military or space applications. In military applications, we expect that there will be some electromagnetic noise incident, especially in case of, say, electromagnetic warfare. And in space applications, where we expect a lot of electromagnetic noise in space anyway. And this ties into how noise tolerant we want the system to be. So obviously, if it's supposed to be a more robust and highly fault tolerant system, then we would want very high noise tolerance. This slide has some examples of EMI effects in real products, and this slide just highlights what can happen when sometimes EMI effects have not been completely understood. Let us now go over a quick review of some laws of electromagnetics that are important in understanding EMI and EMC issues. The first is, of course, Faraday's law, which states that the voltage induced in a loop is proportional to the change in field of flux linked to that loop. The important thing to remember here is that the induced EMF is in a direction that tries to oppose the change in flux. The second important law is Ampere's law, which states that the current in a conductor is proportional to the path integral of the field in any closed path around it. And the final thing that we might possibly want to remember is that the H field is proportional to the B field. And the H field is typically the magnetic field intensity or field strength measured in amperes per meter. And B is the magnetic flux density measured in Tesla. B and H are sometimes taken analogous to voltage and current, but in the true representation, the voltage analog is dB by dt, and the current analog is H. So which means that the flow variable is H, and the effort variable is dB by dt. Let us now look at some EMI and EMC concepts. The first thing to look at is antennas and propagation. We are not going to go into too much detail about how antennas work and the details of antennas, but the simplest antenna is a monopole, which is just a conductor, a single conductor with some fixed length. And the response of this antenna is optimal at lambda by 4, which is called the quarter wavelength. It also has an omnidirectional response, which means it radiates equally well in all directions. Here we can see the relationship between the frequency, the wavelength, and the quarter wavelength for some common frequencies. So 2.4 gigahertz is a common frequency used in cellular communications. And we can see that the wavelength corresponding to this 2.4 gigahertz is 125 millimeters, which is 12.5 centimeters. The lambda by 4 or quarter wavelength for this is 31 millimeters. This means that a piece of wire forming a monopole antenna of length 31 millimeters will be able to emit and absorb energy at 2.4 gigahertz. Now, this is just a quick example to show that a small trace on a PCB, which is very commonly possible, it is possible that it is, say, of this dimension, and if we are not careful, it is going to start picking up energy at 2.4 gigahertz. Similarly, 900 megahertz, which was the old GSM band, has a lambda, which is a wavelength of 0.3 meters, and a lambda by 4 length of 83 millimeters. 83 millimeters is about 8.3 centimeters, and which corresponds to perhaps the length of a cable or a power supply line. And it means that a conductor of this length will pick up energy at 900 megahertz. Similarly, the final one is 300 megahertz, which is a commonly used ISM frequency, and the lambda for that is 1 meter, and lambda by 4 turns out to be 25 centimeters. Now let's look at some noise mechanisms. There are two most commonly used mechanisms to model how noise is coupled. The first is called capacitive coupling and the second is called inductive coupling. Now let's look at this system. Supposing we have a noise source, this is an AC source connected to a conductor. And this conductor obviously has a voltage on it which is Vn. Next to it we have our system, which is what we are using, and it has a wire that runs close to this conductor. Now due to this electric field there's going to be some voltage induced at this point, and as a result this RL is going to see the input signal which is Vs, and in addition is going to see some amount of noise coupled from this noise source Vn. Now the equivalent circuit looks somewhat like this. This C effective is the equivalent capacitance formed by these two conductors and this space in the middle. So this is the equivalent circuit. And we can see that based on the value of this CEF, the value of Vn, and the value of RL, we can calculate how much noise is going to get coupled onto this line, and which will thus be seen by RL. Similarly, when we talk about inductive coupling, we consider a current carrying loop, which is IN, which is the noise current in some sense. This current is flowing in this loop. It sets up a field, and this part of this field links to the system that we are trying to analyze. And depending on the amount of field that couples into this, we are going to have a voltage induced, and that voltage adds to the voltage that we are trying to send across, which is Vs. So the load resistance RL will see not only Vs, which was intended, but a part of Vn, which was the unintended or noise component. The equivalent circuit looks something like this, and based on the amount of coupling, the orientation of these two coils, the distance between them, etc., we can find out M, which is the coefficient of mutual coupling between these two coils. Now let's look at the second classification of noise mechanism, which is conducted and radiated. Now in this situation we have somebody here who's using a hand drill, and as we discussed before, this has a motor, it will have brushes and it's going to radiate and conduct noise. Now radiated noise travels as electromagnetic waves through any medium, and they can travel through walls and don't need line of sight. So this is how radiated noise is being emitted and is being picked up by this television set in the other room. Conducted noise, on the other hand, needs a conducting medium to travel. So any noise or noise voltage at the drill is going to cause a voltage which affects the line through the conductors, and since this television set is connected to the same mains wiring, the AC wiring, this is going to see that noise as well. So this is just a quick demonstration of how conducted and radiated noise works. Now before we go ahead, just a quick summary of the EMI compliance testing process. As I mentioned before, whenever a product needs to be sold, it has to be certified, or it has to be ensured that it complies with the EMI and EMC requirements in force. This is usually done by a recognized accredited laboratory. The standards bodies that I mentioned earlier are also in charge of making sure that these accredited laboratories are following the standards and so on. The test protocol and sequence are very strictly defined by the relevant standards, and these tests can consist of one or more of these things, usually conducted emission, conducted immunity, radiated emission, and radiated immunity, and they're usually done one by one. Now what is pre-compliance and pre-compliance? A product must be tested, as we said, for EMI compliance, and the test procedures are defined by the standards. Now, before we go to the accredited lab or agency to do the actual test, which can be quite expensive and time consuming, designers typically want to run pre-compliance tests, which are some simple tests which are intended to find and fix problems before they show up in the accreditation process, in the testing process at the lab. The idea is that if we catch EMI problems early, it saves time, it saves money, and it saves effort. And a lot of this testing can be done with quote-unquote DIY techniques, and we don't need a lot of expensive equipment. And experienced designers often have ways to estimate the amount of noise being emitted or conducted without using the entire spectrum of tests. These few slides just give a brief overview of how the testing process actually happens. When the device under test or the new product is taken to the lab, they place it in a particular way on an electrically insulated table. It is connected to what is called a LISN, which is Line Impedance Stabilization Network, and a spectrum analyzer or EMI receiver is used to measure the amount of conducted noise that is emitted by this device under test. For radiated emission, a similar test is performed, except instead of using the LISN and connecting to the power leads, we connect an antenna and measure the amount of EM energy being emitted. In this case, we also need to move the product around because the EM energy may not be equal in all directions, as a result of which we need to keep the device under test on a turntable and move it around and see where the electromagnetic energy is maximum. Radiated emissions can be tested both indoors and outdoors depending on the application. And so here is an example of an anechoic chamber which consists of an indoor EM radiation test. And here we have what is called an open air test facility where the testing is done outdoors. So in the next video, we are going to start looking at some case studies and looking at the EMI and EMC issues that can come up in different types of circuits. Thank you.